Hello, my name is Thierry Jeshekam from SS and the University of Luxembourg. I'll present our 2000 journal first paper titled Killable Mutants with Symbolic Execution. This work was performed in collaboration with Mike Papadakis, Maxime Cordy, and Yves Letrao. In a nutshell, this work tackles the problem of automation of test input generation for mutation testing. Mutation is its adequacy criterion, like statement or branch coverage, but that uses artificial poles, also known as mutants, to measure the quality of test suits. To apply mutation testing on a program of test, mutants are generated by systematically making a simple syntactic change on program. Then, coverage measurement on each mutant by a test is computed by executing the same test input both on the original program and the mutant. If the test output differ, the mutant is said to be killed by the test. The ability of a test suite is thus measured by the proportion of mutants that it can kill. Existing test suites are then executed with each mutant and the killed mutants are recorded. If the proportion of killed mutants is not enough, additional tests are generated to kill the remaining mutants. These remaining tests are also called stall mutants. We focus on generating these additional tests in this work, which is known to be a tedious task to perform. Talking about test generation, the three main types of test generation techniques are random, meta-heuristic, and symbolic execution. Each have its advantages and bottlenecks. The technique that we propose is implemented with symbolic execution. Symbolic execution is a program analysis technique that explores the path of a program represented by a path condition and keeps the program state for each path. It starts by setting the program's input to a symbolic value and then it emulates the execution of the program with such input. Because there is no constraint on the input, the execution is started with path condition set to true. As the execution proceeds, the state of each program path is updated by applying the executed statement on the state. For example, here we set n to 0. When a branch statement is encountered, the symbolic execution accounts for both branches and duplicates the execution state and path condition, updating the path condition by adding the branch condition and proceeding with the execution of each branch. For this case, the first branch is taken, is updated with x0 greater or equals to 0. This is repeated until the execution reaches the program output, leading to a full path. The then branch is executed similarly by setting condition x0 is less than 0 until the output as well by updating the state and the path conditions. We observe that there's a path here in the middle which has a path condition of false, which is an invisible path. Then when we have the path condition of each path, then we can use the constant solver to solve each path condition and obtain an input that can be executed to follow the given path. Going back to mutation, how do we use symbolic execution to generate tests capable of killing mutants? Let's first look at condition to kill a mutant. To kill a mutant, a test needs to first reach the mutated statement, create a different program state on the mutant and the original program upon the execution of the mutated statement, and then 3. Maintain the difference down to the output. To generate mutant killing test with symbolic execution, the standard approach is to apply symbolic execution on both the original and the mutant program and collect the path conditions and symbolic output. Then look for an input that follows path overlapping path condition and at the same time output difference. That leads to the following formula that we call the mutant killing condition. Solve this formula for all pair of paths of the original program and mutant eventually lead to a test that kills the mutant if the mutant is killable. However, such approach is greatly expensive. Approaches from the literature leverage the application cost by generating tests right after the mutated statement, as you can see in this figure. Instead of using the output difference, which require the path expiration to the program output, the path conditions and program state right after the mutated statement are used to generate test. We refer to this technique as infection only. Despite that this reduces the application cost, it does it at the expense of the ability to effectively kill mutants. In the previous example that we had, infection only generates tests right after the execution of statement 3, leading to the mutant killing condition x0 less than 0 and x0 not equal to x0 plus 1. When solving this with the Z3 constant solver, the generated input is x0 equal to minus 1, which does not kill the mutant because the output of the original is equal to the output of the mutant. However, if we propagate slightly further before generating the test input by solving the mutant killing conditions, comparing the only relevant path on the original program with the relevant path of the mutant, we get the first pair, an infeasible kill condition. For the second pair, the solver solves the kill condition and return x0 equal to -2, which kills the mutant. Thus, the chances to generate tests that kill the mutant increase. Of course, the cost slightly increases as well. We can see with this that the propagation phase is important to increase the probability to kill mutants. Therefore, we propose SEMu, a technique that allows such propagation. SEMu proposes heuristic to balance the cost and effectiveness of test generation. The following illustrate the heuristic implemented by SEMu. Say we have the following symbolic execution tree of program, where a mutant changes the statement highlighted in red. SEMu heuristic control the precondition of the symbolic execution, defining how to prune path unlikely to reach the interesting places. For example, we can see that the thick green part is place that is part of the precondition. Using existing tests, this can be performed. It also defines a location on the symbolic execution tree named checkpoint, where state comparison between the original program and the mutant are performed, and where further path pruning is performed to allow some path to propagate further or not. This path pruning is also controlled by specifying the type of path prioritized and the proportion of path to prioritize. SEMu also optimizes the symbolic test generation for multiple mutants by sharing symbolic execution path exploration across multiple mutants. Thus, the path prefixes explored prior to mutated statement are shared and explored once. For example, here, there's the exploration of M1 and M2. They all share the prefix, which has nodes 2 and 3. And this is implemented by creating a mutant program that encodes all the mutants that are targeted in the same code. We implemented SEMu on KLEE. SEMu is available open source at the following link. Now we turn to the evaluation of SEMu, where we compare the effectiveness of SEMu, KLEE, and infection-only technique for the same time budget and on the same subject programs. The experimental procedure is the following. For each considered subject program, we use the included developer test that we augment by generating more tests to target statement coverage with KLEE for 24 hours. This forms our initial test suite. Since we are interested in killing stubborn mutants, which are mutants that survive the initial test suite, we execute the initial test suite on the generated mutants and remove the killed mutant. The stubborn mutants are then fed together with the initial test suite to use for precondition to each compare technique for test generation for 2 hours. Each technique generated an additional test suite. We execute each test suite on the stubborn mutant, measure the ability to kill stubborn mutant and compare the achievabilities. To reach any bias linked with mutant redundancy, compute the subdomain stubborn mutants and evaluate the technique based on the proportion of stubborn subdomain mutants killed. As subject programs, we use the Coreutils programs. Each technique targeted more than 23,000 mutants to generate tests. Because of redundancy and mutant equivalence, the 529 stubborn subdomain mutants are used for evaluation. Here are the results. This box plot shows the proportion of stubborn mutants killed by each of the 3 compared techniques. We observe that SEMu kills more stubborn mutants than KLEE and infection only. The difference is more than 20%, and there is statistically significant difference. This shows that SEMu heuristic to control the propagation are indeed beneficial to achieve higher mutant killing effectiveness. Moreover, when we look at the per mutant performance, we see that there are some overlap on the mutant killed by SEMu and KLEE for some programs, outperform SEMu for some programs. These were mainly cases where there is a slight single stubborn mutant, or there are too many targeted mutants forcing SEMu to do shallow exploration. For most of the cases, SEMu outperformed KLEE. Similarly, there are overlap between SEMu and infection only, more than with KLEE. Nevertheless, there are only 5 cases where infection only outperforms SEMu. Moreover, SEMu generated 87% more mutant killing tests than infection only. In summary, we presented the problem of test generation for mutation testing and showed the limitation of existing techniques. To tackle the problem, we suggested the need for propagation and proposed heuristic to cost-effectively perform propagation. We implemented it into a technique and tool named SEMu. SEMu outperformed the existing techniques at killing stubborn mutants. Thanks for watching our paper presentation.
So very soon. So hello everyone, and thank you very much to the authors and videos. Yeah, applause to this journal first papers. I'm sorry I talked to Cherry here on the choppy audio. It might be we listened to it, but we couldn't see it. So, but again, a very interesting paper that you did on stubborn mutants. So I invite you all to help me with some good questions here on this paper. Could you please? So my first questions was really the first question I had is that you have really addressed the input space, not the test cases. That's what you mutated, right?
Yes, the tool or the techniques aims at generating test input.
Yeah,
not testing the program.
Yeah, exactly. And you used symbolic execution. So what was the part of the work that you found most difficult to do in all of the work in this paper?
Well, the most difficult part is, I think it was to implement actually the approach, because it was implemented into KLEE. So I had to first understand the code of KLEE and kind of try to find a way to put it all together inside. And since one program can have many mutants, so we have to think through to see ways to reduce the overhead of the symbolic execution. So we need to find ways to kind of make the mutant share the symbolic execution, and how do we implement it into KLEE and all that. So it was quite a challenge, the implementation.
Okay. So we got a good question here from Pedro Delgado Perez. He says, great work. Did you use the output of the programs as killing criterion, or is it based on assertion?
Oh, yes, we use the output of the programs. So in C program, the C programs that we use are the Coreutils programs, which are like a utility that you can have in a Linux operating system by default on the terminal, like ls, cat, and echo, and such programs. And the way to test them, or an input for, let's say, a program like cut, it can be like cut with a -d and then the delimiter, and then -f, and then let's say the field that you want to access. That's an example of a test input. And now when you execute that, and it will print something on the screen, let's say, and what is printed on the screen is the output, as well as the error code, the exit code that is returned. And then when we execute the original program with such an input, we also execute the mutant with the same input. And then we collect the printed output on the screen and the exit code of the original program and the mutant, and compare the two. And if the two are equal, then the mutant is not killed by that test. If not, then the mutant is killed.
Okay. That's interesting. I mean, the great thing is it's automated. I think
Yes.
that's the big help. But I'm sort of thinking how long time it actually takes to do this. You said it was below 2 hours. You had a limit there, right?
Yeah, the 2 hours was the time limit for the test generation.
Yeah, that you put in the hash tables, right?
Yes. So the SEMu just generate the test input, but during the test input generation, SEMu will compare the states of the original program and the mutants in order to see whether the test has the chances of killing the mutant. And after the tests are generated, during the experimental part, when we actually evaluate the test generated to see what is the mutation score, then we actually separately, not in SEMu, but with a different tool, we execute the test with the mutants to see which mutants are killed by the test with each of the compare techniques.
Yeah. Okay, so you could use this, for instance, to fix patches and so on.
Yeah, absolutely. Since
Uh,
it's like it's sort of differential symbolic execution where we have two types of, let's say, two different programs that we analyze at the same time and look for difference, then it can really be applied for patches. We will
mhm.
have like the pre-commit version, let's say, which is
Okay,
like the mutants, and the post commit, which is like the original, and then generate the code in a form that is acceptable by SEMu, and that way we can generate test.
that's really good. Yeah, there was also Nameng here who had a clarification question. Why is a mutant producing the same output not killed while the mutant triggering a different output is killed?
Well, the mutants that have the same output as the original program for a given test input is not kill, because I mean when the output is same, it's not kill because it shows that the behavior of the mutant and the behavior of the original is the same for that particular test input. And usually the mutant is considered to be killed when there's a difference of behavior with the original program.
Mhm. Okay, did that help, Nameng? Otherwise, write in the chat.
Yeah.
Any other questions from the audience? No? We have been discussing a long time here. What would be a good question? And we just say, oh, it didn't help. You read the paper. Yeah, okay, thanks.
Oh.
But it's really hard to come up with questions on your own work, for sure. And it's also, if you sort of clarification is usually what you need to do. I think actually the idea of that you have to iterate so many times, I'm thinking, isn't it very time consuming to have to do that, to create all the sort of mutants, but you get the automation. Have you tried big programs, many programs? Do you have like a limit on what programs you tried?
Uh, well, the limit is basically the same limit that symbolic execution has.
Yeah.
If the program is too big, it's too big. The number of paths to explore also is very large, and the amount of resources that is required is also increasing because
Yeah.
we need like uh, more time and more memory to actually make the symbolic execution.
But
And
now,
so,
when
yeah.
isn't it that you have like, I mean, you can parallelize the execution. You can use some
Yes.
of the other papers, speed up. You can sort of put it in the cloud and really
Yes.
sort of do a massive. But
Yes.
wouldn't that be a way, like, or is it still an upper limit for you? It seems like it. um for using it in real systems, we're really talking huge programs compared to what symbolic execution can do. So have you planned any further work around that lines to sort of
Well, it's more what is now being done is more about kind of applying. First, your question about the very large program.
yeah,
Usually, if the program is very large, it's probably more useful to use SEMu for
yeah,
testing this particular unit,
yeah,
because the symbolic execution kind of like it works better when the number of paths explored is larger, right?
yeah,
And to be able to do that, it's better to focus on a certain area of the program. So if the
yeah.
program is very large, it's better to kind of look at the certain component that we need to
Okay,
test and focus on that particular component.
yeah.
So
So
now we are,
is this heuristics manual that you decide, or do you need or do you have automated that as well?
yeah, the heuristic, they're just the parameter that can be set manually.
Yeah.
Actually, there's no best heuristic, I think, because it depends on the type of program that we have, the choice of
Okay.
heuristic that work better.
Hello, my name